Okay, so the recording has started. Now I'll share my screen. So hello everyone. This is week 9 of NPTEL CS52 Reinforcement Learning course. I'm Sandarbh Yadav and I'm from CSE Department IIT Bombay. And this is like the Reinforcement Learning course by Professor Balaraman Ravindran of Computer Science Department in IIT Madras. So this session is being held on 26 March 2024, which is Tuesday. So let's begin. So again, like the same details of the weekly sessions, like generally, these sessions are on Tuesday, but the session of next week, like basically might not be on Tuesday. But if there is any change, like as of now, it's not confirmed, but if there is any change, you'll get the notification and it will be held on the same link. Anyone who has taken this course CS52 RL can attend. Again, why to attend discussion on practice assignments and assignments, problem solving and doubt clarification, also to ensure two-way communication. Okay, so again, the expectation is that before watching these TA sessions, you should have watched the weekly lecture videos. So this week, like the topics were basically fitted Q equation, DQN, then policy gradient, and finally, it was like we were doing function approximation with policy gradient. And also in between, we saw how reinforce can be generalized from banded setting to full RL setting. Again, as usual, it is recommended, highly recommended to read the Sutton and Barto book. Also, like the recordings and slides will be made available later. So again, these are the same guidelines. We will follow the same order, practice assignment first, then problem solving. Again, this problem solving will contain questions which are not part of practice assignment or the assignment. And then in between we will have demo also. So today's demo will be, there will be two demos. One will be on DQN and second will be on policy gradient. So these are the two demos which are lined up for today. And the environment which we have considered is the usual card poll environment. And then finally we will move to the assignment. Okay, so these are the week 9 topics, DQN and fitted Q equation, and policy gradient approach was introduced. After that, we also discussed like how this reinforces generalized from banded setting to full RL setting. And in between, like we also saw the actor critic approach, which basically combines policy-based approaches with value-based approaches. And we saw a policy gradient theorem also with its derivation. And then we saw how policy gradient approach can be done with function approximation. So here also we derive the same theorem, but with function approximation. So now let's move to the practice assignment 9. So the first question in practice assignment is true or false. Is DQN guaranteed to converge to an optimal policy? The key term here is it guaranteed to converge? Like it might converge, might not, because like DQN basically is using neural network. Basically, I should say deep neural network as function approximator. So what happens when we are using any function approximator, then we lose some like guarantees. So we are basically compromising on something. So due to this function approximation, it might not always converge to an optimal policy. It might converge, but we cannot say that it is guaranteed to converge to an optimal policy. So this statement is false. Okay. So now I'll move to the next question. Which of the following is true about DQN? Again, another question of on DQN. So this is that it can be efficiently used for very large state spaces. Yeah, like we can use for very large state spaces. Just that we need to have suitable feature of those states. Suppose if our state is like we can think of like 3D space, like and it's suppose it takes continuous values of x, y, and z coordinate, and this is essentially infinite space, and which is very large. So for this, like we can have features like just the x coordinate, y coordinate, and z coordinate, and give this as input to the DQN, and maybe whatever actions are there. Suppose there are two actions in between, like there will be some hidden layers. So based on that, we can get q values for both the actions. So yeah, we can efficiently use it for very large state spaces, because like we have like featureized them, and we can give like this will take any possible state. You can give any possible state using these features. So it can be efficiently used for very large state spaces. Now, in contrast to the tabular approaches, in tabular approaches, basically what would have happened, you would be maintaining a table of state action pair. So this is supposed queue table, and for every state action pair, you will be having one cell. So there, like you cannot do this because like it will go to infinity. So when just Q learning without like deep neural network, like if you were maintaining these tables, then it would have become infeasible to maintain these tables in such large and continuous action spaces. So tabular approaches, like this is the disadvantage of them. This is basically a limitation of them, and this is basically overcome by using deep Q network. So this is the correct answer. And second option says that it can be efficiently used for continuous action spaces. So again, like this, this is wrong because like here, like we are having two nodes because we are having two actions. Suppose if the actions were continuous action spaces, so like basically if action was maybe between 0 to 360-degree or something, it can take any real value in between. So there are essentially infinite number of actions, and we can't possibly have one node for each of the action. So in that way, like we cannot have this. One more approach is like suppose with the state features x, y, z, you can give the action also as the input to the neural network, and just have one like there will be some hidden layers, and finally have just one node in the output layer which will give the q value corresponding to this state and this action. But the issue with this approach is like either way, like when like you q value is something which is intermediate, eventually you'll have to take argmax of these q values, right? Q of sa. So in order to get the like is the optimal action, what is the like action suggested by this queue network, you need to take this argmax over all the action. But when you have to take argmax, then this argmax has to be over all possible actions. Then in that case, you will have to make infinite calls to this neural network to get those infinite number of values for each possible action. So in this way, like it becomes feasible in this architecture also. So in both these architectures, like it is not possible to efficiently handle continuous action spaces in DQN. So this is like one of the limitation of DQN, that it cannot be efficiently used for continuous action spaces. That's why we introduced something called as policy gradient approaches, which work very well in continuous action spaces. So now I'll move to question number 3. This is very simple one. Which of the following is the correct definition of average reward formulation? So if you have watched the lectures, you can simply get this. So is this the correct definition of average reward? Like it has to be, it is missing that 1 by n factor, right? This is wrong. And okay, so I think like there is some typo here. This is not, this is conditioned. This also is conditioned. Okay, so limit n tends to infinity expectation. Again, this is also missing this 1 by n factor. So this is also wrong. And limit n tends to infinity 1 by n expectation of R1. Like this is having that 1 by n factor, but the issue with this is like it's not have conditioned on pi. Like these rewards cannot be randomly generated. These rewards have to be generated by following pi. So again, this is also wrong because this is like corresponding to pi policy. So you have to generate these rewards by moving according to pi. And last one is 1 by n is there and it is conditioned on pi also. So this is the correct answer. So correct answer is third. I think there is something in chat. Maybe I'll check. Yeah, good evening. Welcome. So probably due to Holi, like many people might be on vacation. So either way, like we are recording the session. So let's move to the next question, which is question number 4. So question number 4 says policy gradient theorem does not hold for average reward formulation. Like, is this true? So basically, like I think it wasn't mentioned in lecture that the theorem which we derive, like it is known as the policy gradient theorem. So that is the like name given to that theorem. It is known as policy gradient theorem, and we kind of derived it for the average reward formulation. So this is like basically false. Like policy gradient theorem does not hold. It actually holds for average reward formulation, and we like kind of proved it also. Also, like not just that, that it also holds for even discounted reward setting. But again, like for this setting, like we didn't do the proof, but maybe you can check in some papers. This proof might be there if you are interested. Now I'll move to the fifth question of this section, which is the last question. So basically, it says that how many outputs will we get from the final layer of a DQN network? And this is the number of states. This is the number of actions. So how many outputs we get from the final layer of DQN network? Is it like for SA? So basically, like what is a DQN network? Like basic DQN network, you have like features here. So number of inputs will be number of features of a state. And finally, for each action, you can have a node there, right? So you get Q value corresponding to that state. Suppose two action are there, Q S of E2. So this is the equal. In between, there are some hidden there. And so this is definitely incorrect because we don't get that for each state action pair, we don't get. This is like in tabular approaches. In tabular approaches, we have that many Q values. But in DQN, the outputs are different. Number of states, definitely not. Because Q values, we are dealing with Q values. So output is with respect to action. Action, this is the correct one because we get like one output for each action. Even if like this, I have like more than one neural network, but you can have maybe if you have two action, you can have two different neural network. And then basically I should write number of action. And for each neural network, you can have one node as output, then get the Q value. Then all these Q values like for from each of those neural network, you can merge in one final layer and get like as this many number of outputs. So in this way, like this is the correct answer. Again, this is also wrong. So I hope like you got this. Now, like this is the last question of this section. So I'll move to next section, which is problem solving. So again, in problem solving, like basically like we have moved to topics which don't have like much to solve by manual calculation. So basically like now most of the things will deal with codes and all. So mostly it's theoretical questions, no calculation based question in these topics. So again, like this is the question. So this says that which among the following. So again, it's a multi-option correct. Uh, but again, like like multi-option correct also, but need not be like that. It has to be all the option, like more than one option can be correct. Now in multi-option also only one option can be correct. So we will analyze each of them. So which of the following are advantages of using deep Q learning methods over other learning methods that we have seen. So what is the basic advantage that deep Q learning method offers? So is it a like faster implementation of Q learning algorithm? Definitely not. We are using neural network. So deep Q learning basically uses deep neural network, and we have to train them in like tabular approaches. Like what we were doing is we were simply doing one lookup. We were going to that cell and fetching that value. But in neural network, you have to perform inference. So once you have trained the network, you have to pass the state features, then get the according you will get the Q values. So in that way, like it's not really a faster version implementation. So this option is wrong. Again, like second option says that it guarantees convergence to the optimal policy. Again, like we have seen a similar question in previous section also, it doesn't guarantee convergence. might happen, but we cannot say that it will guarantee convergence to the optimal policy. Because like there are many issues with this. Maybe like our function approximation is such that our neural network is such that it can never reach that optimal policy. So it might also happen. And secondly, like when we are using function approximation, so we are like compromising. So there, like we cannot say like we are guaranteed to converge. So again, this option is also wrong. So third option is obviates the need to handcraft features used in function approximation. Yeah, obviates means basically removes. So it removes the need to handcraft features used in function approximation. So you remember like deep neural network, what happens like you can pass just the raw data and they will learn features from themselves and eventually like you will have the Q network there. So with suppose parameters theta there. So deep neural network have this very good capacity of learning features. So we don't need to handcraft features for them. So you might remember the case of Atari games. Atari games like entire like screen of the game was past pixels, entire pixels, and it basically learned features from that. Like in those pixels, there might be some ball, some pole, so all those things. So we didn't like mention explicitly like that. These are the features that it at this coordinate the pole is there in current state. So the deep neural network like kind of learned all that from the raw features itself. So it removes the need to handcraft features. So this is correct. So fourth option says allows the use of policy algorithms rather than on policy learning schemes. So deep Q learning is basically based on Q learning. So again, like it's off policy, but does it like it's like allows the use of policy algorithms. Off policy, like we can do with plain Q learning also. Deep is not needed really, right? So it's not an advantage, something which is provided by this deep Q learning. So this is again wrong. So like it is a feature of Q learning itself. So it allows the even Q learning allows that. So you cannot say like this is the advantage of deep Q learning. So I hope like you understood this. If there is any doubt, you can ask me. Otherwise, I'll move to next question. So the next question is this one. Value function based methods are oriented towards finding deterministic policies, whereas policy search methods are geared towards finding stochastic policies. Is this true or false? Like basically this is true. So in value function based methods, suppose we take DQN itself. So what will happen? You will have features of state, some hidden layer again, and some action, suppose two action, and you will be getting, suppose state is S, you will be getting as A1 and Q of as A2. Then what happens like you take argmax over this, and then you will get the policy. So generally, like most of the times, what will happen, like when you are using this neural network, like it will give output in floating representation, suppose 0.621193, this much, and 0.723456, suppose this one. So the possibility of a tie becomes very less in such scenarios. So basically, like when you take the argmax over these Q values, it's most of the times like one of the action, only one of the action will be having the maximum value. And that tie possibility is like very less. So it is like basically geared towards finding the deterministic policies. But what happens in policy search methods? Suppose we consider a policy network. So what will happen in policy network? Suppose we have this policy state and it will give maybe suppose we have two actions. So suppose it's assigning some probability 0.25 or 0. Remaining probability to this action, maybe 0.75. So so basically like you won't be taking max over this, right? There is simple probabilities. What you can do is you can simply use some stochastic kind of policy here, like 0.25%, like 1/4 of the time you can take this action and 3/4 time you can take this action. So like this is like this comes naturally, whereas here like there is a thing where you are taking argmax because these q values are something intermediate. Eventually you will act according to the policy. So this is the difference here. Here, like probabilities, like although like here I have used like something between 0 and 1, but it could be Q values could be well above 3.14 something and 9.14, and even it could be negative also. So you can take softmax to convert it to some probability kind of thing, but either way, like that's not the natural thing to do. So there are Q values. You essentially take argmax, and that possibility of tie is very less here. So you can say that they are guaranteed, like oriented towards finding deterministic policies. Although it's possible that they can land up in stochastic policy also, but mostly they are oriented towards finding deterministic policy. And policy search methods like here, like it's naturally coming out as probabilities. So you can like simply have a stochastic policy. Suppose if you are in some state pi s, you can take with 1/4 probability action event and 3/4 probability you can take action event. So because like there is no concept of argmax here, we are already having a direct mapping to the policy. Okay, so if there is any doubt, you can ask me. Otherwise, I'll move to the next question. Maybe I'll check in chat once. What is we get converged value of what if we get converged values of policy parameters? So basically, like if you have converged to the what if we get converged value of policy parameters? I don't know what you mean by this, but like it might happen that you might converge to the optimal policy if like optimal policy can be represented by the policy network. Otherwise, like it might happen that you might not converge to the optimal policy itself. So whatever policy you converge to, like you will act accordingly. So policy parameters here like are basically weights of the neural network. Policy is no more stochastic. No, like once you have trained for the like you will be training for some amount of time. Once you have trained for that amount of time, and what will happen is like you will stop the training. Then you will move to the evaluation phase. So once you have stopped the training, at that point, like all those weights will get frozen. So it's no longer like non-stationary weights. So the weights are like now fixed. So once you have trained, then you basically cannot use the term stochastic in that sense. It's like something non-stationary or stationary. So what if we converge to the values of policy parameters, can be claimed that the policy is no more stochastic. So you can say policy is no more non-stationary, but it can still be stochastic. Because like suppose if your maybe I'll show in this example only, if your policy converts to something like this after training, like this action like for some state it's giving 0.25 for action A1 and 0.75 for A2, then you will simply act like 0.25 with you can like generate a random number between 0 and 1 and see if it's less than or equal to 0.25, you go with action A1, otherwise you go with action A2. So it can still be stochastic in that sense. Okay, yeah, got it. Okay, so now I'll move to the next question. So again, this question is simply from the lectures. Only if you have attended the lectures, you can see it if FW approximates QPy and is compatible with the parameterization used for the policy. And then this indicates that we can use FW in place of QPy in the expression for calculating the gradient of the policy performance metric with respect to policy parameter because, like, is that because like q pi minus FWSA is equals to 0 in the direction of gradient of this one or this one? So the answer is this one, right? Q pi minus SA minus this one equal to 0 is in the direction of the gradient. And why this happens is because the error between this one, this is basically the error, and it is orthogonal to the gradient. So if it's orthogonal to the gradient, when you project something at orthogonal basically means 90 degree. When you project something on like with angle 90 degree, it will be like 0 in that direction. So again, B and C are the correct options. So now I'll move to the last question in this section. Again, I mentioned that like mostly it's theoretical questions here, like because you won't be doing manual calculations in when deep neural networks are involved. So most of the time it will be quotes and all. So the last question says that suppose we use vector critic algorithm described in the lectures where QPy is approximated and the approximation used is compatible with the parameterization used for the actor. Assuming that use of differentiable function approximator, so this means that you can calculate the gradients and all. We can conclude that use of such a scheme will result in convergence to a global optimal policy. Again, like we have seen this enough number of times, whether it's DQN or something else, like we cannot guarantee the convergence to a global optimal policy because like here, the issue is like we are using function approximation, and approximation basically we are losing, making some compromise. We are losing some information there. Maybe it might happen that our like whatever parameterization you chose, it cannot represent the optimal policy itself. Or maybe like if the set of policies which is represented by this one, your neural network is pi cap and the actual set of policies is pi. So it might happen that this is a subset of this set. So you cannot say that even it might happen that your optimal policy, suppose one of the optimal policies pi star, it might happen that it belongs in this set but not in this set. So if it's not represented in this set, then you cannot say like it can guarantee convergence to a global optimal policy. So this cannot happen in function approximation setting. But as we have seen in the theorem, that convergence to a locally optimal policy is possible. So this is possible. So this we have seen. Again, like the third option says that cannot comment, but this is also wrong. We can converge to a locally optimal policy. That is fine. So basically what happens is like there is a space of policies. Suppose this is the your suppose parameter space below, and this is your policy, like how good a policy is like on y-axis. So your globally optimal policy resides here, but you can converge to some policy here, you can converge to some policy here. So these are locally optimal policy. So you can guarantee convergence to a locally optimal policy. Obviously, a globally optimal policy is also a locally optimal policy. So you might converge here also, but not always guaranteed to converge here. You might sometimes you might converge here also. Because like we are using gradient descent methods. So in those methods, basically convergence is at some local optimum. So with this, like we have come to the end of this section. Again, like there are two demos for today. So the first demo is on DQN and second demo is on policy gradient. So essentially like we will devote a lot of time to demos in this lecture. So maybe I'll start sharing this. So someone can confirm if you are able to see the browser. Yes, sir. Yes, sir. Okay. Okay. Right. Right. So again, like just a refresher of the environment. So here also like we are using the cardpool environment, and we have already seen this in fitted queue equation also, and some of the previous demos also. So what happens in this is like this environment is, so this is provided by this gym, and again the action space is discrete. You can, so basically what's happening in this environment is you have to stop this pole from falling. So this pole can be, initial state can be anything. So it could be aligned in something at some angle, and you have to like move the cart either left or right so that this pole doesn't fall. So this is the goal of the game. So action spaces, you can either move left or right. So this is the action space. Observation space is again in this range. So basically like there are four features of the state, and these are its range. So first feature is, so basically I'll show you the features. So cart position, like it could be some coordinates, and cart velocity. This can take, so minus 4.8 to 4.8. Maybe you can think like 0 is somewhere here and minus 4.8 is here, 4.8 is here. So this is the cart position coordinate, and the cart velocity minus infinity to infinity. So initial cart velocity, like, or cart velocity at any point of time can be anything, any real number. So that is also there. But also like like we cannot use infinity directly. So like basically what this means is that this velocity factor, the smallest value it can take is this, and the largest value it can take is this. So this is basically the limit of the Python variables, like how large a value or how small a value it can store. So this is the range. Now, third feature is again pole angle. So this is from minus 0.418 to plus 0.418. So this is in radian. Again, so radian you might know like it's another measure of angle. And so this minus 0.418 corresponds to minus 24 degree also. And again, the last feature is pole angular velocity. So this cart is moving in a linear direction, so it's having velocity this, but this angle has angular velocity because it might be like going down or going up like at some angles. So it has angular velocity again that takes value in this way. So minus infinity to infinity. So this is again the first like array corresponds to minimum values and second array corresponds to maximum values. And this says that the number of features are 4 and all are like float 32. So this is basically the maximum and minimum value of this float 32 variable in Python. And this is the way we import this environment card pole. So again, the action space like 0 corresponds to you can push the card to the left like here or push the card to the right. So this corresponds to one action. So there are two actions. And what are the rewards? So for every step taken, so the goal is to keep the pole upright for as long as possible. So every time step, like you will get +1 if pole has not fallen, and including the termination step. So threshold for awards is 500 for version 1. So basically, like this is the maximum award which you can achieve in one episode. So this is the maximum reward, the maximum total reward. So here, like gamma is, you can assume gamma to be 1. So it's undiscounted problem. And starting state is like this, like it is assigned uniform value in this way, minus 0.05 to 0.05. So all for all four parameters. So the initial values will be in this, and the episode ends when like any of the following occurs. Termination, like basically the pole angle is greater than plus minus 12 degree. Basically, this means that no matter you take go left or right, like the pole is going to fall. So this can result in termination, or it might happen that the card position is greater than plus minus 2.4. So basically this means that the card position has reached the end of the screen. So this you have reached, the card has reached here also, left or right, like episode will terminate. Also, another, like it might happen that the card remains in this position, like center only, like doesn't go left or right, and the pole also keeps on balancing. Then you will need to have one more criteria so that like episode terminates. Otherwise, you will be simply staying in this position no matter like what happens. So in that case, like we have this truncation criteria. If episode length is greater than 500, so basically they are saying that the left length of a episode is 500 time steps only. And in each time step, if you are able to hold the pole like without falling, you will get reward of +1. And that's why like that maximum reward possible is 500 for each time step. So this is like the brief description of the environment again. Now for all the like tutorials and demos, we will be using this environment only. So again, like for DQN also, like I have taken this notebook from the RL Summer School, the website I showed you last time, same website, and even the notebook is contributed by the same person. So essentially, like this person is like he has contributed to stable baselines, which is like one of the most popular library of RL algorithms. So most of the implementation of RL come from stable baselines third version. And here, like this is just the installation. So some dependencies also. And again, like so there are basically two notebooks here. First, this one and this one. So in this one, like first notebook, like we will be writing components of this DQN one by one. And like there are basically three components: replay buffer, network, and the exploration policy. And in this notebook, like we will be actually doing the training using the functions which we have written in this notebook. So this is basically to write the function solution. So as you might remember that like this replay buffer is like one of the important component of DQN, and it is basically used to collect the transitions so that like we can have a fixed data set just like FQI. So you remember in FQI what was happening? We were like having started off with some initial queue, not, and then generated data from that, and then on the basis of that data we trained one regressor, and then we generated data from that regression again. This kept on happening again and again, and that's why we call it fitted queue iteration, because we are fitting a regressor using queue learning. And however, like compared to FQI, this ring buffer is consistently updated with new experience. So basically, suppose if you have like, maybe I'll open Jamboard. So suppose this is your buffer. 3, 4, 5, 6, 9, 10. So suppose you have like you can store 10 transitions at a time. So initially when you collect data, you will store first transition here, 0, then 1, then 2, then 3, then 4, then 5, then 6, and 7, then 8, then 9. Okay, you will store in this way. And what happens like when you reach the 10th transition, you will like drop overwrite this transition. So this basically initial transition, whatever was stored here is gone now. So you have replaced it by this 10th transition. And in the same way, like you will keep on overwriting them. So there is like it's very small size, but generally buffers are like 500, or you can take even 1000 or even 2000. That's like basically depends on how much memory you can afford to use. So basically like this is what the point was mentioning, that you can override the old transitions. You are essentially throwing away the old transitions and replacing them by the newer ones. So this is the one. And one by one, like you can like keep on sampling from this replay buffer and use it for the updates. So here like in fitted queue iteration, we were using the entire data set, right? But here, like you can sample mini batches. So mini batches, basically, if your mini batch size is equal to the size of the data set itself, then essentially you can say that you are using complete data set. But if mini batch is just one, like you are using just one transition, so you can like have any number in between those two numbers. So you can either go with like one or two. You can choose like whatever batch size you prefer. And generally, like this is a hyperparameter, so it depends on the problem also. So you need to tune it. So it might happen that some batch size might work on one problem, but it might not work well on another problem. So you need to try out different values of this batch and see like which one works better. So again, like this is a class replay buffers. So it is having like 5 arrays. And like these are like storing like the observations basically, as I have mentioned before, also it basically means state. So this is the state now. So this is the current state observations array. And the next observations is the next state. Like basically you can say this is S and this is S dash, and this is actions and this is rewards. And it also stores one more array which is known as whether the episode has terminated or not. So basically what is happening, you are having 5 arrays here. Suppose if we consider array of 100 length, and this one is storing 100 state. So the way you will be reading this data is, suppose at 0th index, this is suppose action, this is state, this is action, this will be S dash, suppose S dash, and reward also, and maybe terminated, something like this. So one transition will be like first element of all these 5 arrays. So this basically means that whether you have terminated. So it might happen that episode has ended, so you need that information also. So this is also stored. So, but your transition is mainly this S, A, R, and S dash. So in this way, like you will be moving your iterator from 0 to first one, and correspondingly like you will get one transition. So this way like the authors are storing, but like you could have used a dictionary or something, some other data structure also, that's fine. So in a way like I'll be sharing this notebook with you so you can like modify and use your favorite data structures. But again like you'll have to modify other things also so that the things make sense. So again like these are the imports. So this is the like replay buffer class. So it has a init function as usual. So here, like I hope like you guys are aware with object-oriented programming concepts. So we will be using classes and associated functions. This basically makes the code clean and reusable. Also, there are many benefits of using this object-oriented approach. And so this is the init function. So when this init function is called, one instance of this class will be created. And what is getting passed in this init function is buffer size. Like what is the size of the buffer? It can be, you can pass 500 size or whatever. Like, and it's also passing observation space and action space. So this is coming from the gym environment. This is just to store. So basically like also in init function, you will like I mentioned this. So you are indexing in this way. So you need to have this current index, like at what like index of the array you are. So for that, like they are using this current index. So initially it will be 0. And another variable is self dot buffer size. So buffer size is equals to buffer size, whatever comes you will pass while instantiating an instance of this class. And then finally, there is another variable is full. So currently it's false because there is no transition, but like eventually when the buffer is completely filled, then you will set it to true. And again, this observation space and action space is also stored. So here, like we are creating like these values to store. So self dot observations numpy dot zeros. So buffer size into observation space shape. So what happens here is like although like your buffer size is 1,000, but as we know in cardboard problem, like there are four features. So you will essentially need something like 1,000 into 4. So this is happening here. So you are initially having zeros for all of them. So you will be having 1,000 into 4 because there are four features. And next observations also similarly you will have this. And again, the action is simply an integer, 0 or 1. 0 means left, 1 means right. So you don't need that, like 4 here. So here it's just 1,000 into 1. And in similar manner, you can create the rewards. 0, just the buffer size. Again, its reward can be an integer, but here they are using float, so that's fine. Terminated, again, you can use just a Boolean variable. So it's true or false kind of. So initially you have initialized all of them to zeros. So this is what the init function of this replay buffer class is for. If there is any doubt in this, you can ask me now. Otherwise, I'll move to the next portion. Okay, so now the second function is store transition. So what happens like once you have seen some transition, you want to store this transition in the experience buffer. So how to store that? So you will be passing observation like basically current state, next state, action, reward, and terminated. This is like a set one transition is getting passed here, and you need to store this in the buffer. So what you do is you can like have this self dot observations dot current index. You can put it here, and next observations current index you can put it next observation like next state, then put the action, reward, and terminate it. So you are already maintaining this variable, right current index. So initially like there was nothing, so it said 0 index, it's not filled anything, 0 is also empty. So whatever like first time you call this store transition function, like it will simply fill those value at the 0th index at this index. So all five values go in that index. But gradually, like you need to now increase this index. So now it will move to this one. So next time this function is called, it will put place the things here. So in this way, like this thing is working. Also, you need to have a check that if current index is equals to buffer size. So if like you remember like in Python and almost all programming language, our indexing starts from 0 and goes to n minus 1. So if your buffer size is all low, Suppose if your buffer size is n, if its current index is already n, so that means like now you are out of your buffer. So what you will do, you will go back to this and replace the original one. So essentially that's happening here. So if your like current index is equal to buffer size, so you also need to update this variable is full. So initially till now it was false, but now it has become true, and you will set the current index to 0. So this is happening here. So if at any point of time you reach the end of the buffer, you come to the beginning of the buffer. And like now from now on, you will like overwriting these transitions. So these are like old transitions. So in this way, like old transitions are getting removed and new ones are taking their place. Either way, like the order doesn't matter because you will be sampling randomly from this replay buffer. So you can store it here. Now the third function and this is sample. So how to like once you have this experience replay buffer, now you need to sample from this buffer. So how you will sample? So there are two possibilities here. Again, like you might need to sample at some point of time when the experience buffer is not filled itself. Maybe like if the size was 100 and maybe you have only 50 transitions stored, but at that point also you need to sample because like we are using online. So here like you can have this. So upper bound is basically like this basically returns if it's full, then it will return the self buffer size. Otherwise, it will return the self current index. So this basically means if it's filled, you are returning like whatever is the buffer size. And if it's not filled, it's returning this index. So this is the upper bound. And in this upper bound, you are basically generating random indices. Also, one thing to note is like we are sampling with replacement. So with replacement means like suppose if you are having uh an and in this like some balls are there, red, blue, or whatever. So you are sampling one ball and keeping it back into the and like again like there is a possibility that you can draw that ball again. So in this way like you can draw samples, like number of samples can be larger than the number of balls in this arm because you are doing with replacement. If you were doing without replacement, then the maximum number of samples you can get is equal to the number of balls. But this way, like since we are sampling with replacement, it might happen that the samples which we draw from the experience replay buffer can be more than 100 because we are doing with replacement. So again, like, so it will basically generate some. So here, like one more parameter is coming in this function. You also need to specify what is the batch size you want. So batch size is basically like what is the number of samples you want. So once like this np.random randint is generating that many number of indices and corresponding to that indices, like you are returning these observations s dash a r and terminated. So this sample function will basically like sample from this replay buffer and return those replay buffer samples. So I hope like this is clear. So maybe I'll check in chat once. Current index equals to current index plus one. Yeah, yeah, like it's just one of the way of implementing things. So you can try out like different kind of things. Like maybe the author like that way. So now like this is basically so since like this is not this notebook is not a complete notebook. So here they are using some assert statements and all. So to check whether like everything is fine. So import gymnasium again like just they have imported the cardpool environment buffer size initially they set it to 1000. Okay, this is the maximum buffer size and they have like made the instance of that class. Remember that class we declared. So an instance of that class is this buffer, and you are getting this observation from environment reset. So this is basically your start state from the environment. Once you have the start state, now what you are doing is this is simply a equator. So for this underscore in Python, you can use this as a variable name also underscore, just underscore without any character after it. So for underscore in range 500 and you can have action. You are basically so initially like for checking they are using just a random policy. So this sample will return any action And when you have the start state, you have the action also. Now you will take that action in the environment and you will get the next observation, basically next state and the reward. Also whether the episode has terminated or truncated, whatever. And so once you have got this transition, now you have all four, five components, right? So you have the current state, next state, reward, this terminated thing, and action also. So what you will do is you will store the transition. And this function we have already defined, store transition. So you pass all these five values there and it will store in that buffer. Now we move to the next state. So current state becomes the next state, and now again this for loop executes again. But before that, like we also check whether like done is terminated or truncated. So this is like simple or operation between two boolean variables. So if like any of this has happened, like done would be like if it's done, then you will like essentially reset the environment and start the episode at the beginning. So this is what is happening here. If episode ends, then you are again like getting a start state from this function. And now one thing to notice is that our buffer size was like they declared the buffer size at 1,000, but we are filling only 500 transitions. So essentially, like we are in the middle of the buffer. Buffer is not filled. So we are basically checking alert not buffer is full. That buffer is not full. So alert basically like it throws an error if like this condition is not met, but this condition is met here, so there is no issue. And it's also checking buffer current index is 500. Yes, that's also true. Now you are using the sample function of the buffer to sample like 10 buffers, 10 like transitions from that, and you are checking that whatever is returned by this, is it like the size is 10 and all those shapes kind of check. So like these are just checks. Now like we again check one more check. So here like remember like now we have already stored 500 transitions. Now we are storing 1,000 more. So buffer will get filled also and initial 500 will also get overwritten. So again same thing here and simple checking like whether the buffer is full. Here in this case buffer will be full because we have not only like filled it completely. Suppose it was like 1,000, then 500 have been filled. Initially it was 500 filled. Now we have 500 filled here also, and the next 500 have replaced the initial 500. So that is what has happened here. And now they are checking all its conditions that whether the current index is now 500. Yes, it's 500 and samples buffer. So remember I mentioned this thing that you can sample something more than the size of the buffer itself because we are going with replacement. So similar to this example, you can sample more than buffer size also. So you can sample 1,001 transitions because the buffer size is 1,000 and 1,001 is more than that. So you can sample that also. And they are simply checking whether the length returned is same and action are same. So now comes the second component of this, which is the queue network. So similar to fitted queue network equation, the queue network estimates. However, instead of taking the action as input, it outputs. Okay, so basically they are giving this as an architecture thing. So basically they are following the architecture in which like the output number of output nodes are equal to number of actions. So in this case, like there are two actions. So you can say like the number of output nodes are two. Again, like just imports. So in this, like they are using PyTorch. So again, you might know like PyTorch is from Meta. So like many researchers are now moving towards PyTorch from other framework because it's quite simple to use. So again, so this is the class your queue network, and I'll show you like you don't need to in PyTorch you don't need to write much of the functions. It happens automatically. Maybe we will see this later. So init function, basically you are giving the observation space, action space, also number of hidden units, how many like hidden layer nodes you want. So in each hidden layer, there will be 64 nodes. And also in neural network, you will need to have this activation function. So you are having ReLU. ReLU, you might know already. It's rectilinear unit. So maybe I'll show you the graph of ReLU. So it's kind of hinge. less than 0, it becomes uh, 0, and then from then onwards, it's linear. So it's like essentially max of 0 comma x. So that is the linear activation function which is getting used. But you can use something else also apart from ReLU. There are many sigmoid and all. So here they are using ReLU. And again, like observation dimension is basically 4. So this will give 4. Number of actions will be 2. This will return 2. And this is the network which they are using. So you see, like it's so simple to define the network in simple way. So first layer is linear. So basically your initial input nodes will be 4 because there are 4 features of the state, 4 into 64. So this is one layer. Then next layer will be 64 into 64. And again, like both layers will have activation function in between. And in last layer, we are having 64 into number of actions 2. So this is our neural network. So maybe I'll show you what our neural network looks like. 4 nodes, this is input. Then there are like 64, 64, 4, then again 64, and finally 2. So all like connections are there. You can make those. So this is how the neural network looks like. So again, like remember at last layer, they don't have any more activation function because linear is fine. Because we are generating real values. Q values can take real values. So linear is fine here. Now this is the forward pass of the neural network. So remember, like if you were using some other framework, you might have to do np dot dot, like you will have to take the dot product, add biases and all that. So this simple function qnet, you just have to pass the states and it will return. It will calculate the forward pass and return you the outputs. So this is the forward function in PyTorch. So this is like basically you have defined, you have like basically use the PyTorch forward function and use it inside your own forward function. So when you call this forward function, you simply need to pass the states and it will return the actions, like not actions, but Q values corresponding to actions. So again, like just the testing of this. So they have generated one instance of this Q network class, printing this. So here you can see like input features are 4, output feature 64 bias. Again, you might know that this sometimes what happens, like apart from just the weights, like like this node will be getting connections from all other nodes, and you can add one more term W0. So this is the bias. So as of now, like we are using bias term. So bias is 2. And like no grad means like basically they are not using gradient calculation. So because we don't need it here. So we are doing no grad. So here like they are making some observation tensor and passing that observation tensor to this and getting Q values and simply asserting like whether the shape and all is fine. It should be 1 into 2. So this is the shape, and best action you can take argmax. So this is basically returning 2 Q values corresponding. So there are 2 nodes in our neural network. It will return 2 Q values corresponding to this one, and you take argmax over those Q values and is instance best action int. So here they are also checking that whether it's int. Now, third component, important component is epsilon greedy data collection. So sometimes people think that since we are like already using neural network and all, we don't need to follow epsilon greedy approaches. But that is still needed because exploration is always needed. Because if we are simply following the policy greedily, then it might happen that we don't explore a significant part of the state space. So in order to ensure that, you need to use this epsilon greedy. So this is quite simple. So here, like QNet passed, you pass the observation state. Basically, state is getting passed and exploration rate. Generally, like this is the value of epsilon. You can have like 0.1. So with 10% times you are exploring, otherwise 90% times you are being greedy with respect to the action which is having the highest Q value. So you are basically exploiting in that case. And action space size and all. Device, like here, like this is one special feature. If you have, like I have not connected, but Colab also provides GPU. So if you want to do faster computation, you'll need to set up CUDA and you can have it as GPU. But then you also need to ensure that your code is optimized in order to use GPU. So as of now it's CPU. So again, like this is the simple, they are generating a random number, and if it's less than 0.1, suppose, then like they are taking random action, otherwise they are taking a greedy action. So greedy action basically means that they are passing the observation and getting the Q values from the neural network and taking the argmax. So this is the action. So and they are returning this action. So if like you are exploring, then a random action is getting returned, otherwise like the action with the highest Q value. So this all like you can, and so this was quite simple in fact. So again, like this is one more function, collect one transition and store it in the replay buffer. So this is like now we are like building the parts. Like basically we are collecting one transition from the environment and storing it in the replay buffer. So you are getting environment here, Q network, replay buffer also. Everything is coming as input, exploration rate. So if you don't pass it, by default is 0.1. And but both basically like int 0 means you are not printing anything. But most is like some kind of logs. So here what is happening is action. So basically you already defined this epsilon greedy action selection. You are getting an observation here. You are passing that observation and Q network and exploration rate action space. And basically like it will return you a action. It could be greedy, it could be exploratory. You are already passing this exploration rate. So it will be according to that. Then once you have the action, you can take that action in the environment and get this next observation reward and terminated or truncated, whatever. And then you are storing this into the replay buffer. We have already defined this store transition function. So in this replay buffer, you are passing all these parameters and it will get stored in the replay buffer. And again, then you will move to the next observation. So also you need to check whether you have terminated the episode or not. If you have terminated the episode, then you need to reset so that a new start state comes to you. And basically like this function is basically returning the observation, which is the currently like this is storing the next state. So it might happen if like a episode has terminated, it will give you the start state. Otherwise, it will give you the next state. So this is what this function is doing. Now like they are again testing this. So I mean like you can see QNet is initialized, buffer is initialized, and this for I in range 1000, they are calling this function and testing it. So just the buffer index and all those checks are there. So this you can see like no error is thrown because like all these checks pass. So one more thing you might remember is like we generally yes, I'll show you. So you might remember that we generally decay this epsilon, right? We don't have like it's 0.1 suppose for the entire period. So suppose we might start at initially we want to explore more one and then we want to decay it to at some point we might make the exploration part 0 and simply keep on exploiting because maybe at 10,000 steps we have explored enough. So now we are focusing only on exploiting. So this kind of like how this exploration rate goes down, this is encoded by this function. So this is like kind of optional, you can see, but there is not much happening here. You are basically having a max steps, like this is the max number of steps, and you are passing the current step on the basis of that. It's like basically it's decaying linearly. So what is happening here is like it starts off with one, and basically like not one exactly, like they are actually having some start value also. So here, like you are also passing this initial value and final value. So on the basis of that, it is generating like in this proportional to this current step upon max step. Whatever you are in, like it's decaying accordingly. So here, like you can see one example. So initially they have set the exploration rate to be 1.0, and finally they said that eventually, like after this many number of steps, exploration rate should be 0.01. So it will decay linearly during this time step, and it will decay from 1.0 to 0.01. So for n steps equal to 100. So this is happening. So they are calling this linear scheduler, and they are eventually checking if initially like that at step 0 whether the exploration rate is this. So it is returning this only because there was no error, and they are also checking that whether the exploration rate after this all these calls is like equal to the final ones. So this is happening 100 times. So after 100 steps, it will decay to 0.01. So again, like in this notebook, we have basically written the main functions, how to create replay buffer, how to sample actions according to FNGD, and how to create a queue network. And in like this part two, like we will like use all of this information to actually do the training and how to implement the training. So this is the second notebook. So again, like the environment and all remains the same. Again, installs and all. So maybe I'll check chat once if there is something in chat. Okay, nothing. So I'll move to so imports and all. So these are there. So basically, like in this here, like we are updating. So here, like they are using two kind of DQN. One is without target network. So this is basically what was discussed in the class, and one is with target network. So this basically target network actually generates the targets for us. This we will see later, but first let's see this without target network. So this is the DQN update without target. So what we are getting past is QNet optimizer. So there are different kind of optimizers, items and all, like whatever you have initialized, you can pass that. And we play buffer also one instance of that batch size also, and gamma is the response input. So we are basically what we are doing is sampling the replay buffer. So we define this sample function. So batch size is something how many transitions you want. So that batch size is going in the sample function and it will return that many transitions from the replay buffer. And we are like simply converting into tensors. Now what happens? So here like we do not need to compute a gradient. So we are simply basically like you remember in Q learning, we have to calculate that TD error. So we need first we need the target also, and secondly we need the our current estimate. So on the basis of that we make the update, right? So here like in this whole block, like we are calculating the targets. So you might remember the maybe I'll write the Q learning. So the target in Q learning was max over some actions and whatever your next state, right? Suppose n is the variable that which knows so and then a. So this is your target. So basically, like this is getting calculated in this bar. Okay, it was this one. So basically, like we are getting the Q values for all the actions, and here, like we are using the one with the highest value. Next Q values also. So basically, what is happening? Computing the Q values for the next observations. So for next observations, we are getting those, and we are calculating for those actions. And also this should bootstrap basically means that like sometimes we have reached the end of the episode. Otherwise, if we haven't reached the end of the episode, so what happens basically is suppose if you are at the end of the episode, so your basically your whatever reward will be there. That is it. You don't have this gamma factor times next value because the episode has terminated. You don't have a next state. You are moving to a terminal state, and its value is zero. So in order to ensure that they have used this one, so this basically is the kind of boolean. So this is your target. This is the simple target reward plus gamma times next few values. That's it. And this is basically how they are getting is they are simply taking for the state, like whatever next state is there, all the this comes corresponding to all the actions, and then you are taking max over that. That's it. This is what our like this update was. So this is it. And this should bootstrap is just to ensure that whether we have terminated or not. If we are at the end of the episode, then this essentially will be zero. So this entire term will go away. We will be left with just the rewards. So this basically we have now got the targets. So now once we have got the target, we can calculate our current estimate by passing the observations. So this is our current estimate Q values. So current Q values you can like gather like what are the current Q values. So this is corresponding to actions which are actually done in the collection process. So although this will return corresponding to both the actions, but we since we want to do it in that manner, we want to collect the errors only corresponding to actions that were actually taken. So this function gather is doing that. So it basically takes only those actions that were actually taken. So at every point, every time step, we have like two actions. But we don't want, if we haven't taken zeroth action, then why should we consider zero action? We will take update corresponding to only the first action. So this is what it's doing. And we are simply squeezing it in dimension one, and then finally you can have this. So this is just to that whether there is some broadcasting error or something. Since nothing came out, which means these checks are passed, so eventually they are using MSE loss. So this is the MSE loss, current estimate minus target. So target we have already calculated, current estimate is this, and squared and mean, so MSE. So mean squared error. So this is the loss, and again, you can reset the gradients. And this is what I was talking about, that how PyTorch makes life easier for you. So initially you have reset the gradients to zero. Then this is basically calculating the gradients. So sometimes what happens, there are already some residing gradients. So you want to ensure that those are zero. So this makes that them zero. Then you are computing the gradients. Once you have computed the gradients, you can make the updates. So this is doing that update. So remember, you don't have to write the all those equations explicitly. PyTorch is doing that for you. So you just have to make sure that the loss and all are properly defined. So it will do it for you. Now they are basically testing it again, some kind of, they have this environment Q network optimizer. They are using Adam with learning rate of 0.001. So all these concepts of Adam and all, they are from deep learning course. So you might have taken already taking a deep learning course. So these concepts might be familiar to you of optimizer and all. Replay buffer also one instance. And here we got the start state. And again, you remember this collect one step function we defined in the previous notebook. And they are checking for 1,000 range and trying to do some gradient steps. So this is just to test. Now here comes the actual training, final training. So this will basically combine everything which we have done till now. So this is the final training. So maybe we'll go over it one by one. So what is getting past environment, replay buffer size? So remember, till now we were using toy examples. So we were using maybe smaller buffer size. Now we have big buffer size, 50,000. Exploration initial 1 and exploration final 0.01. So here they are actually decaying the exploration rate. Number of time steps is also 20,000. So remember why I'm not executing this, because all this training will take a lot of time. So maybe I have already trained it. So I also have the outputs and all I'll show you. But you can try with different number of time steps and all. And so basically these are the default values. So when you call this function, if you don't pass the values, these default values will go there. And update interval, after how many intervals you want to do the update. You don't want to do it at every time step also. So this is maybe after every 2 time steps you make an update. Learning rate is this, batch size 64, and gamma discount factor again. So after how many episodes you want to evaluate. So maybe here they are evaluating after every 10 time steps. And this is the so this is the number of evaluation episodes, and this is the evaluation interval. So they are evaluating on 10 episodes, but after every 1,000 time steps. And evaluation exploration rate. So in evaluation, they are not exploring as of now. So this default is 0. Seed is basically fixed so that you can replicate the experiments and get the same output every time. So this is an important concept if you are publishing research papers and all, because you want to fix the seed, and in order to replicate the results, you will fix the seed again as 2023 and rerun the experiments and you will get the same value. If you don't fix the seed, then on every run, these randomized algorithms will give you different answers. And again, this device is commented either way. So this is your main training function, and this will return a trained Q network. So again, you have fixed the seed and you have made this environment, and the other thing just and you have fixed the seed of action also, and creating this environment. Then you have reset this everything. Seed is there, fixed seed. Now you are creating the queue network. So this again, like we have already seen, this is the queue network class we have already defined. So you are passing this, and this is one instance. Optimizer Adam as usual, replay buffer is there. You have instantiated it, and now you are basically getting the start state. Once you get the start state, now you are actually doing the training. So for twinning, like again, like since we are using linear decay, so they are getting the exploration like values of epsilon using this function linear schedule, which we have already seen in the last notebook. And now they are like basically collecting one step. This function also we have seen in last notebook. So this will return the next state kind of thing. And you are getting this observation here. And if like these are simple checks, if current state is not like this modulus with respect to interval is equal to 0, then only you will perform the update. So here, like I think they were performing after every 2 times steps. So this update interval. So after every 2 time steps, there is an update. Otherwise, like you don't perform update at every time step. You can change that value also. And this function we have already written about. And also like this is for the purely for the evaluation purpose. So you remember like current step evaluation interval was 1000 there. So after every 1000 steps, they were evaluating. And number of evaluation episodes was 10. So this is also getting passed there. And after all this training, like it will return a QNet, 20 QNet. So this is like after this is basically the definition of the function. So it will be executed below. So this is the function which is getting called here. One DQ and no target. Okay. So I hope like you don't have any doubt in this. So this is our function run DQ and no target, and it is getting called here with environment ID. And just the environment ID is passed. For others, like it's taking their default values. Also, environment ID also has a default value, so you can even not pass that. So once that is done, now like the evaluation starts. So remember, like we said that evaluate after every 1000 steps. So remember, like this is the card pool environment. So the maximum reward which we can get is close to 500. Exactly 500. So let's see. So after 1000 steps, we were getting around reward 9.20, and this is the standard deviation. And gradually, like as how many steps we were training. So we are training for 20,000 steps. So you can see like gradually like we are getting better and better. So mean episode reward is getting increasing. So 400, 300. So there is some variance here. Like one time it went to 400 and came down. But eventually, like if you do it for a large number of steps, then like it should eventually get maybe above 400. Obviously, we are not asking it to converge because it's TQN. So you can try maybe this was for 20,000, but you can try for maybe 50,000 time steps and see like what happens. So so also like there was a video also. So currently I'm not connected to the runtime, but eventually like this code will generate a video for you, and this will be at this location, so you can like gradually move to this location and find this video without any target. But now the important thing comes, which is usage of target network. So remember, like in our function, like we were manually calculating the target here for this one. So, but sometimes what happens, like this leads to instability. Some stability issues are there because like we are using the same network to calculate the target also, and same network for calculating the current estimate also. So sometimes like people use another separate network, which is called as target network to generate the targets. So our original DQN, which is for the estimates, current estimates only, like it will have this theta parameters, and meanwhile, like we'll maintain a target queue network with theta dash, and it will give the output as this one. So like these two networks are used. So this is basically target network is like basically producing the targets for which will be used by this treatment. So almost similar. just difference will be like, remember there we were actually calculating those R plus max this one entity. So this entity we were calculating manually, but here like they are using the outputs of this Q target net. And again, like on the basis of this, they are calculating the target. So it's essentially like we are using two different networks, one for getting the targets, another for getting the current estimates. And similarly, on the basis of that, like this bootstrap we have already seen, we are getting this target, and again, like loss function will be there. Just only difference is that the targets are now coming from another network with different parameters. And this is like not like completely different, but slightly lagged, like a delayed copy of the Q network. So that it improves the stability. And everything else is almost similar. So this is the loss function. Again, like this, you are resetting the gradients to zero, computing the gradients and making the update. Again, like there's not much change in this DQN, run DQN function, and almost similar kind of things. Just that some more features coming, learning starts and all. This you can see, there's not like there are a lot of comments, and because we are like almost out of time, there was another demo of policy gradient, but I think like maybe I'll do it next time. So np.random feed, like all those things are there. So here like, but one more thing you need to ensure that you need to update both these networks also. So that is also happening. Create the queue network, create the target network, and all those. So also like for this example, like they have used another environment which is known as the Flappy Bird. So here like they are training this. Firstly for card pool, then we will move to the next environment. So this you can see like, so that we have trained for 20,000 steps without target, but this they are training for 50,000 steps. So now you can see some convergence here with the usage of target network. This was the like maximum reward which we could have gotten, right? 500. And like after some time steps, like 40,000 time steps, it almost reached 500. So maybe like you can increase the number of steps for that without target one to 50,000 and see what happens, whether it also reaches 500 maximum mean reward. So basically this means convergence. So also again, like similarly, you can go, a video will be generated. Maybe I have those downloaded from my ones. I'll show you. So these are the videos at this location. You can find them. Again, like the last thing is this training of DQN on Flappy Bird. So this game you might have seen it somewhere. So what happens in this game is like some poles keep on coming and you don't want to touch these poles, because you touch these poles, then the game gets over. So you need to pass it this way. So basically, like by default, it due to gravity, it's going down. But yeah, you need to decide whether you need to flap your wings, and that is the action basically. So the environment is like at this location. Maybe you can read it, but basically I'll show you. Like these are the state features. A lot of like state features are there, but the action spaces just two actions: either do nothing or flap. So, and the rewards are like plus 0.1 for every frame it stays alive, and plus 1.0, like plus one reward if it successfully passes a pipe. So here it passed two pipes, so plus two. And if it dies, then a reward of minus one. So these are the rewards setting in this. So again, like this is simple install of this environment. And again, like we are running this declare function on this. So as you can see, like gradually, like the reward is improving. So initially it started around 9,009, then I, so again remember like now the training is like getting more and more. So now we are training for how many steps? Essentially 5 lakh steps. So initially it was 20,000, then 50,000, then 5 lakhs. So this is why like I'm not able to run it live, but either way, like after 5 lakh steps, you get, so it's not converged yet. despite running for 5,000 steps, 5 lakh steps. So you can like run it even more and see like, or even play around with parameters and see like what happens. So again, you can find the video. I'll show you these videos. So going further, like what you can do after this is analyze the learned queued values, whether like they are making sense or not. And you can explore different values of target update, use soft update. So basically here hard update is there, but you can do like some kind of some within some portion of the old value and like basically have some portion of the new value. So that is known as soft update. So you can use some other loss function. Here we use mean squared loss. You can use this hover loss, smooth L1 loss function. So these are norms, right? L2 norm loss, and you can use L1 norm loss, but there might be differentiability issues. So in order to do that, you can use the smooth version of it, which won't have any differentiability issues. Play with different environments. So cardpole and this one, bird one, Flappy Bird was just two environments, but there are many other environments you can play with them. And remember, with same as the Atari environment. So in this Flappy Bird, uh, they have extracted some features from the frame and passing that information to the network. But you can simply use something similar to Atari games and implement a convolutional neural network. So just pass the raw frames. There's like one instance of this. One entire frame goes, then the next frame goes. So you can just pass the raw pixels and use convolutional neural networks. So all that you can try. Basically, you can see how those people that are using Atari games have done, and you can do it similarly for this Flappy Bird or Pong from Pixels, and you can implement DQN extensions also. So there is double DQN also, prioritized experience replay. So remember, like in our version of experience replay, all the transitions have similar priority. No one is given extra priority, but like there are versions where like you can prioritize some transitions. Some transitions might be important for you, but others might not. So you can try out these prioritized experience replay. You might remember like I have shown you that blog spinning up. So here like you'll find not many of these. Uh, Those in introduction, I think. No, no. It's key kinds of RL. So this is hindsight experience replay. There is prioritized experience replay, rainbow and all. So you can try out like all those algorithms also. Like, but this is something advanced. So you can try out those. And again, like in this notebook, we have seen how to implement this TQN algorithm. So maybe I'll show you like those videos once. After that, I think policy gradient, we might do it later because there is not much time for that. But I'll show you those videos first. So maybe I'll share this screen. Can someone confirm if you are able to see this video? Maybe write in chat or something. Yeah, okay, fine. So this is like without target. So this is the DQN for cardpole environment without target. So see like how it goes. So this is what it has learned. See, it is going to the left and the episode terminates. Again, started at some position and it has also learned to stay in between, but it's slightly drifting up. Like this time it's towards left, one time it went towards right. So now it goes there. So these are the three episodes. Now let's see like what happens with trained like with target network. So this is with target network. So you see like this is like kind of more optimal behavior. It's staying in between. And in this way, if it's staying in between, it will actually get that plus 500 reward because that then the episodes will go for entire 500 time steps. Otherwise, if it's going, then it might terminate before 500 time steps, maybe at 300 or something. So this is like more optimal behavior. And this we have achieved with target network. And now I'll show you what happens with that Flappy Bird. So this is like what is had learned for Flappy Bird, but again, like it didn't convert, so it might make mistakes also. So the episode ended because it touched up again. So it hasn't like learned the most optimal one also yet, but you can try out different parameters and see. Like basically, this is not an easy environment. This is a hard environment. So again, now what I'll do is, I think maybe I'll go back to the slides again. So now can someone confirm whether the slides are visible?
Yes, sir. Visible, sir.
Okay, okay. So like again, like maybe policy gradient, I'll do it next time. But I hope like you understood this DQN because this is like this is basically started out this deep reinforcement learning revolution with those Atari games performance. Like there are basically a large number of Atari games. I'm not sure how much. Maybe suppose if 40 games are there, then on like majority of like something around 26 games, this DQN actually achieved performance better than humans. So this is where like it became popular because like it was surpassing human level performance on many of these games. On some games, although it lacks, but most of the games it was having better performance than humans. And this is like one of the main goal in game-based RL because like there the goal is to achieve better performance than humans through these agents. So now I will move to assignment 9. So I think like before moving to assignment 9, so this is like week 9, right? So whatever like basic RL was there, it has been covered in these 9 lectures. From now onwards, like lecture 10, 11, and 12, those are like something advanced topics. So these two are like hierarchical reinforcement learning, and this is form DPs, partially observable. So like in this NPTEL course, these are the topics in advanced topics, but in some other course, you might find some other topics also. This is hierarchical. And so, but this course is slightly old, around I think 2016. So, basically, like there is one more topic, deep RL. So, if you are interested in this as advanced topic, this you might have to do it on your own. Deep RL, maybe like look out for some course or read from blogs, OpenAI, spinning up. I showed you that list. Like there are a lot of algorithms which came up much after these lectures were recorded. So you can try out those also. So either way, like since we go into policy gradient, I will be doing policy gradient in next lecture alongside like hierarchical. I'm not sure whether like I'll be able to get demos of hierarchical reinforcement learning because that is something which I'm also new to. Okay, so with that, like let's move to the assignment. So assignment first question is true or false for the following statements. Again, I won't give you exact answer, but the first statement is DQN is an on policy technique. Is it an on policy technique? Like DQN is basically based on Q learning. Like basically Q learning, you use function approximation, and this function approximation is equals to deep neural network. Then you get what is known as DQN, and you have that experience buffer also. But the main equation remains the same. Remember, I showed you that equation in Jamboard, right? Max, this is the target calculation. So for some state, this is our target. So if this is the target, and like you have that R plus also gamma times. So this is the entire target for you. So, but this thing remains same, and this makes it off policy, right? Because SASA is on policy. So there are actually some deep versions of SASA also. You can check them out also. I'm not sure the name, but there is something like deep SASA. You can try out like some versions of that deep approximator function approximator versions of SASA are also there. SASA is on policy, but DQN like basically Q learning is off policy. If Q learning is off policy, then DQN is also off policy. So it's wrong to say that it's a non-policy technique, right? And actor and critic is a policy gradient method. Is it a policy gradient method? So, like basically, like we started out with policy gradient methods and had that baseline, right? Now, if we use like instead of returns, remember at one point we reached in the derivation that we were using these returns. Instead of returns, if we start using value functions, returns of the trajectories, then like we move to this regime of active critic. So it's essentially a policy gradient method, but like which uses concepts of value function based methods. So, but the main architecture driving force is the policy gradient itself. So you can say that active critic is a policy gradient method. Just a special kind of policy gradient method. Generally, like people say that these are like two kind of approaches: three value based, policy based, and people generally say that active critic are a third class. But essentially, like it's under this policy gradient, but it uses concepts of both. So major concept is policy gradient, but some concept of value-based functions, value-based methods is also there. So again, like second statement is accordingly you can get the answer. So now, if there is any doubt, you can ask me. Otherwise, I'll move to the next question. So what are the reasons behind using experience replay buffer in DQN? So this we have already seen in the demo also. So this is again multi-option correct. So maybe I wanted to ask you guys, like, did you receive any information about the exams or something? Like, when are the exam of this course?
Not yet, sir. Not yet.
Okay, okay, okay. So probably like I'm actually I haven't taken NPTEL course like before this, so I don't know how these guys work. But I'm not sure whether there will be MCQ type of questions or like some handwritten kind of question. So I actually don't know. So maybe like this is an important thing to keep in mind. Like generally, like these circles means single option correct and squares means multi option correct. So I'm not sure whether it's pen and paper based or something else, but they might not indicate. So you can, if it's computer based, like you need to go on the screen and fill, then definitely it will be, you need to know this circle is single option correct, square is multi option correct. If it's pen and paper, they might indicate. So what are the reasons behind using experience replay buffer in declare? So basically it's asking like what is the kind of advantages provided by this experience replay buffer? First is random sampling from experience replay buffer breaks correlations among transitions. This we have already seen in lectures. Remember, like there was a strong correlation. Like if we like don't use, we keep on like using updates at we make updates at every time step, and there might be like some strong correlation. And in order to break that correlation, we randomly sample from the experience replay buffer, and that correlation breaks. And this correlation basically causes issues in convergence. So we actually have to break this, and this is one of the reasons why experience replay buffer was introduced. So this is correct one. Now the second is it leads to efficient uses of real world samples. So basically, like if you are not using experience replay buffer, so you see some sample S A R S dash, you use it, update it, and you then throw it away. So it's kind of use and throw. So you use once, in fact, use once and throw. You don't store it. So, but in experience replay, we buffer like you are actually storing for maybe at least some time. Maybe like if your buffer length is very large, maybe 1 lakh, 10 raised to power 5, something, then what happens like you are essentially storing for a long time. So you are not instantly throwing away the real world sample. And sometimes what happens in real world applications like these samples are hard to get. So you cannot afford to lose those samples easily. So in many problems, like there are issues related to less samples, like samples available are very less. So in those cases, it makes sense to actually store those samples, not throw away. So it leads to efficient usage of real world samples. That is also one of the reasons. And again, like it guarantees convergence to the optimal policy. So this is DQN. So you have already seen questions like this before. The keyword here is guarantees. So again, like with function approximation, you cannot say guarantee. With some compromises already there, and these guarantees are lost. Whatever existed in Q learning and all, so those are lost here. So maybe too local, you can say, but not too global. So again, like this, you can figure out on the basis of obviously it won't be none of the above. So third option on the basis of that, you can figure out the answer. So I think there is something in chat. MCQs will be there. Okay, if you, so MCQs will be there in your question, then either way, like it's better to practice MCQs because sometimes there will be some options which might look they are right, but they are actually wrong. So that closeness is there. So MCQs basically means that they might force you to make mistakes. So you need to be careful about that. And sometimes what happens, you do the entire calculation correctly, and at the last moment you make some small mistake and you get the answer wrong. So be careful about all those issues. Also, like there will be time limits. So in these like assignments and practice assignments, you are getting essentially 1 week time. So you can take as much time as you want, and you are having these sessions also, but there will be time constraint also. So you need to manage all that. Basically, my point is like be prepared. Yeah, both circle and square options will be there. Yeah, right. So multi-option correct and single option. So yeah, that's it. So if there is no doubt in this question, I'll move to the next question, which is question number 3, which says, so its assertion and reason. DQN is implemented with current and target network. Okay, so this question like directly comes from our demo itself. We have already seen DQN is implemented with current and target network. Yeah, it can be. So, and using the target network helps in avoiding chasing a non-stationary target. Remember, like when we were using the same network, suppose with theta parameters, and we have another target network with theta dash parameter. So targets were also in, if we are not using a target network, so then in that case, our targets were again coming from this network, and our current estimate were also coming from this network. So it's kind of non-stationary target because target itself is moving. Because target is also coming from the same network. You are getting the target and current estimate also. So it becomes kind of non-stationary. So in order to have a stationary kind of target, you use some other network, delegate version. So you have this, so that targets are slightly stationary. So using target networks helps in avoiding choosing a non-stationary target. So this is also true. This is also true. Uh, this can be not necessarily easy, but nowadays, like most of the implementations actually use target network. So you can say like this is also true. Just you need to figure out whether the reason is the correct explanation of the assertion. So if there is no doubt, I'll move to the next question. So policy gradient methods can be used for continuous action spaces. So remember, like we discussed DQN. In one of the questions we discussed like why DQN is not like kind of its limitation, right? Continuous action spaces. And there I mentioned that policy gradient methods actually are a better choice for continuous action spaces because they can directly map to policy. Suppose how this will happen. Suppose you have a again like X, Y, Z coordinate. These are the features. And suppose your action is continuous. Maybe you want to predict the velocity or something, and in between there are hidden network. You can simply predict a real number here. No issue. You that can work with continuous action spaces. So you can simply predict the action. This is basically what is policy network. Policy is the mapping from state to action, or even sometimes if you are using stochastic policy, then simplex over this action. So either way, like if you are using deterministic policy, then you can simply predict the action here. And there's no concept of arguments or something like which was happening in DQN. So you were getting the Q values corresponding to each action, then you were taking arguments over that. So either you have infinite number of nodes in the output layer, or if you were passing the action also as the input, then you will have to call this network infinite number of times in order to get this argument because this argument is overall action. So all those issues were with DQN, so which made it not suitable for continuous action spaces, but policy gradient methods they can be used for continuous action spaces. Just one thing to ensure that it should be differentiable, right? But I like there are other approaches which even if you can use with non-differentiable functions also, because basically like we need this gradient because this gradient is needed for updates, right? For gradient, we are using gradient descent updates for neural network or gradient descent if you are using loss. So for that, like you need, but there are methods which don't use gradient updates, gradient information, and like some example I'll give you CMAES. Or there are some other basically what is gradient ascent or gradient descent? It's an optimization algorithm. So there is a search space and it's finding the maybe local minima or local maxima, depending on whether you are giving descent or ascent. But there are other optimization methods also which work without gradient information, like CMES is one of them. And there are some more methods like uh, evolutionary computation methods like the genetic algorithm. So all those don't use gradient information. So in that case, like it can work even if it's not differential. But the only good thing about these policy gradient methods is that it works, can be used for continuous action spaces. So this is true. Either way, like if you want to try out these methods also, you can see like these methods basically don't require gradient information. So if your function like objective function and all is not differentiable, then you can switch to these methods. These don't require gradient information. Uh, Adams is basically it will require gradient information because it's a kind of optimizer eventually. So it works on like all these RMS prop, Adam, and there are some more optimizers. They require, I think, gradient information. So now let's move to the fifth question. Again, an assertion reason. So this is actor critic updates have lesser variance than the reinforced update. So this we already know. Like reinforced, like one of the biggest issue with reinforced is its variance itself. Like in fact, like many people like don't like this reinforced because it has a lot of variance. So assertion is true, right? Ectocritic methods have lesser variance. In fact, like you remember in reinforced, we introduced the baseline, and then like in ectocritic, we use value function based approaches. So generally, like these ectocritic methods have lesser variance than reinforced updates, and also like reinforced updates can like the reason they have this large amount of variance is because they use the entire trajectory, and when the trajectory gets long, very long, then there is a lot of variance. So this is true, definitely. And the reason they have given is actor critic methods use TD target instead of GT. So GT is the like MC return, like full return, and TD target, like actor critic methods use TD target instead of GT. So this is also true. But only thing you need to answer is like whether like this is the correct explanation of this. On the basis of that, you can figure out the answer. So if there is no doubt, I'll move to the next question. Okay, so choose the correct statement for the policy gradient. Remember, like I was mentioning, that I think like Sir missed that point that it's actually known as policy gradient theorem. So this is quite popular. So, and they are asking for average over formation. So dou p pi upon dou theta, is it this summation over s, summation over a dou pi? What is missing here? Q pi is missing. So this is wrong. Again, like this, I think you should be able to get from the, if you have watched the lectures only. This is summation over s v pi of s, summation over is this, like this thing you need to take care, like whether was it b pi of s or some steady state distribution like d pi of s. So again, this will be wrong. So again, like there are two options left. So on the basis of that, you need to see like whether this is correct. If this is correct, this will be the option. Otherwise, none of the. You can see like from your notes or whatever, like you can rewatch the lectures if you remember. Otherwise, you can see like what is the correct equation of policy gradient for this ability work formation. This has been derived, so you should already know it. But either way, you can see the answer based on that. So now we move to the seventh question. Again, a multi-option correct. So suppose we are using a policy gradient method. to solve a reinforcement learning problem, assuming that the policy returned by the method is not optimal. Okay, so it has returned something policy which is not optimal, and which among the following are plausible reasons for such an outcome and why it could have happened. So remember, like I discussed this already, like if the set is pi dash and this is the set of policies which can be represented by our function approximator, and this is the actual set of policies which should be there. So sometimes like our function approximation cannot represent all the policies, and the optimal policies might be in this set but not in this set. So this is one of the reasons. So obviously, like let's see one by one. So an optimal policy, so this is definitely true. This I have explained. An optimal policy could not be represented by the parameterization used to represent the policy. So that can happen. Again, this is ruled out. So search procedure converge to a locally optimal policy. Yeah, like it can happen. So obviously, like locally optimal, this means that it's locally optimal, but not globally. So it might happen, because like the guarantee is only to converge to some local optimal, maybe not to global optimal policy. And this option is the search procedure was terminated before it could reach an optimal policy. So yeah, this you can do it manually. So generally what happens, like you saw something analogous in carpool environment also. If like our cart was like constantly like in the between and the episode was not getting terminated, then they set a limit of 500 timestamps. So sometimes like if like due to computational issues, like you have like maybe you can run that much time and that much resources only. So you want to put a limit that if you cannot reach an optimal policy within that time, then I'll terminate the algorithm and be happy with whatever you converge to. So this is also a construct. So it can happen that the search procedure was terminated before it could reach an optimal policy. So you can set some termination criteria. Maybe like some of the popular termination criteria are, remember like we in our algorithm also we set like number of steps as 50,000. Why we set it to 50,000? Because we kind of said that this is what we want to compute for. Maybe at 70,000 it might have landed in. So this is basically a construct which we use. So it might terminate before it has actually reached the optimal policy. So this is like just one of the termination criteria. Some other termination criteria can be like, so it's like changes are not happening. Like the reward was like, remember in one example, like constantly after many episodes, the reward was 500. So basically we have converged, but we were still doing those evaluations. So we could have stopped at that point. So maybe we can see if in consecutive steps the reward is not changing, and like we can stop that. Or we can say like if we know that 500 is the optimal reward, if we are like within some maybe plus minus, obviously not plus, maybe we are near 495 and we can terminate. So this could be another termination criteria. So it might happen that the search procedure was terminated before it could reach an optimal policy. So this is also correct. So now I'll move to the eighth question. So eighth question is again true or false. Monte Carlo policy gradient methods typically converge faster than the actor critic methods, given that we use similar parameterizations and the approximation to the Q pi satisfies the compatibility criteria. Okay, so basically the main statement here is that Monte Carlo policy gradient methods converge faster than the actor critic methods. So remember, actor critic methods were using TD kind of thing, and these are using Monte Carlo. So these are essentially waiting till the end to get those returns. So how can they converge faster than the actor critic method? Actor critic methods are doing bootstrapping. So you cannot say that Monte Carlo policy gradient methods typically converge. Maybe in some case it might happen, but not always. You cannot say typically. So again, like based on that, you can get the answer. Now, maybe I'll check once if there is anything. Okay, so then I'll move to the next question. Question 9. Okay. So question 9 says when using policy gradient methods, if we make use of the average reward formulation rather than the discounted reward formulation. then is it necessary to assign a designated start state as 0? Is it necessary? Remember, like if we were in this discounted reward formulation, we were having this fixed sum start, designated start state, and from that we were calculating the long-term reward just to have this raw measure of some policy by. But the question they are asking is if we use average reward formulation instead of this, and sometimes like if some designated start state wasn't there, there is a set of states. So then we were like having this imaginary state, and we can with this imaginary states we can land in any of these things. So this was happening in discounted reward formulation. But the question they are asking is like if we use average reward formulation, is it necessary to assign a designated start state? So what is the like definition of average reward? Limit n tends to infinity 1 upon n r1 plus r2 plus whatever rn, and this should be sampled according to pi policy, like all these rewards. So does like any of so key thing here is this n tends to infinity. So this limit is when n tends to infinity. When we are like moving, we are like doing our calculations at this long time. Then what will does it really matter whether we started at S0, S1? Everything will converge to the same if we are using this limit. So it doesn't matter like which start state we started with. S3, anything can be start state, all will like kind of converge to the same value. This is happening because of this infinity. So if we make use of average reward formulation rather than this, is it necessary? I don't think so. So based on that, like you can get the answer of this also. So with that, like we will move to the last question. So last question says true and false. Exploration techniques like okay, so one exploration technique is softmax. Another we already saw today as greedy. So either way, like one possible extension to that one is like dequant demo is like you can use softmax instead of Epsilon grid. So if you want, you can try out. You remember the softmax, like how it was E of something and upon summation of over E of other action. So you can try out like those kind of in which like you assign probability to each of the action, and on the basis of that probability, it's not like basically like this Epsilon grid is like you are giving like sometimes what happens is 0. Suppose the probabilities are close 0.25, 0.24, 0.23, something, and in this way, like so that it sums to one. But like it would be like kind of unfair because this is very close to this action. But still, like you are taking being greedy with respect to this action only 90% of the times. So in such cases, like it makes sense to use softmax. So you can try out those exploration techniques like softmax. And the question is exploration techniques like softmax are not needed for editing. Okay, so this we discussed in code also, like they are still needed. As and the question says, as the randomization provided by experienced replay provides the sufficient exploration. This is wrong actually. Because like the randomization which is provided by the experienced replay, it doesn't break this correlation. Like it is used to break the correlation, right? Suppose if our policy or state space is very this, like this, and we are like you having this policy and we don't explore enough, so we might be doing something even if we have experience with it, we will be doing this kind of thing, exploration. So this region only we will be exploring, but all this region, like this will be unexplored if we don't take other action. So maybe like if some action was here, then we could have put on there and explore something like this, and maybe like this. So experience replay, like it is used to break the correlation, but it is not a replacement of like this exploration. So you cannot say that if you are using experience secret, then you can simply avoid these exploration techniques like softmax or epsilon greedy. But one thing you can do is you can like we did in this one, you can start with some initial exploration and decay it to some small value, so that you don't want to always explore. Like you are exploring, but with very small value. So this kind of thing. So this says that is it not needed? Like this is false, right? So it is actually needed. So also like this DQN is simply like a function approximator version of Q learning. So you can think in that way also. Like, does Q learning like require exploration? Yeah, like it requires exploration. Otherwise, like we will be getting stuck with some initial policy we started with and some nearby policies. So you can think that way also that exploration is always needed. Okay, so with that, like I think like we have come to the end of this section also. So what this is the policy gradient chapter from Sutton and Bartow. I think like from now on I'm not sure whether Sutton and Bartow will be followed for the next lectures, but like this chapter you can read on policy gradient, and there are some notes also, like these are from the NPTEL lectures only. Maybe someone formulated these notes and uploaded on Google Drive. So those are there. So this is the link. You can click on that and you can go to that link to see that those notes. Okay, so maybe this is the link. Okay. So yeah, that was it from my side. So if there is any doubt or something, you can ask me now.
Yes, sir. Thank you very much, sir. Thank you
Okay,
so
okay.
much,
Yeah,
sir.
yeah, welcome. So okay, so if there is no other doubt, then we'll meet. Maybe I'm not sure like whether the next session will be on Tuesday only, or it might be on Sunday. So I'm having a clash on Tuesday. Let's see like if it happens on Tuesday. Otherwise, like if it happens on Sunday, you will get advance information. So that will be there. Okay, so that's it from my side. So let's meet next Sunday or Tuesday, whatever. Okay, then I'll stop the recording.